Okay, in this video we're going to take a look at a couple of examples. Again, this is the second video, so hopefully you already watched the first one where I explained what a probability density function is. In this video we're going to talk about how to use them. So the previous video gave examples of how to know whether or not something was a probability density function, so I'm not going to repeat that in this video. We're going to jump right into some examples where we're actually using them. The first example is a calculate the probability type of example. It comes from the first edition of the book that we use in AB calculus. So this is a topic that book covers, although our book does not. And so here is our first question. It says that suppose you find an old clock up in an attic. It stopped running long ago. What is the probability that should this really happen, the clock stopped somewhere between 2 and 5? Okay, so because it's an old clock, I'm assuming that means it's one of these analog style. And so if we wanted to have stopped between 2 and 5, then what that means is that the hour hand is pointing somewhere between the 2 and the 5. And so the hour hand is somewhere over here. Now, the way we would have approached this problem back in geometry class is we would find the area of this sector, we would find the area of the whole circle, and we divide those two areas out to figure out the probability. But that's not the approach we're going to take right now. Instead, what we're going to do is we're going to develop a probability density function, and then we're going to use that probability density function to calculate the probability that the hand is somewhere in this region here. Okay, so now let's think about this. The way clocks work is, assuming it's been wound, it runs forever. Obviously, the nature of the story is such that it stopped running at some point. But no matter when it started running, until when it stopped, no matter how long that was, the hour hand was always pointing at something between 1 and 12. Okay, it was always somewhere in between these two things. And so what we've got is this situation where it could go all the way before 1 even, right? So we could say all the way from 0 to 12. Now, obviously, the hour hand can't point at a 0 because there's not a 0, but it can point at a 12. And so what we've got is that this is one situation that the hour hand is going to point all through those. So when the clock first started running, the moment that I wound this clock or put in batteries or whatever, these were the different things where the X could be pointing at. Okay, but then I got to noon or the next day or whatever, and time continued to go past 12. But the hour hand still stayed in between 1 and 12, or 0 and 12. The hour hand didn't move to a 13 o'clock. And so what I have is that after 12, I have the same set of possible outcomes. Okay, so same after that. Okay, so what I've got is this type of a scenario that it can point at a particular hour from 0 to 12, from during this interval, and then it can, after that interval, it still points at the same hours from 0 to 12. Okay, now let's talk about, so what's the probability that's pointing at a specific hour? So what's the probability that's pointing at something before 1 o'clock, between 12 and 1? Or what's the probability that's between 1 and 2, right? So just, we're talking about what is just between those two times. So what's happened? Well, if we look at all of these things, these hour sections, they divide the clock into 12 parts, right? So it could be between 1 and 12 and 1. It could be between 1 and 2, 2 and 3, 3 and 4, etc., etc., etc. And there's 12 sections of where it could be. And so for it to be in one section, it's going to be there for a 1/12 of the time. So what I have is this scenario where our function is going to be somewhere between 12 and 0, right? Somewhere between 12 and 0. And it's going to be there And then it can't be anything else. It can't be anything else. So this is the type of probability density function that we're working with. So it can't be anything except for one of these intervals. And those intervals, strictly speaking, are happening between midnight and noon. But then between noon and midnight, it's the exact same intervals, and so that doesn't change. We can maybe think of this as being like a modular arithmetic type of problem, but this becomes our probability density function. So it can't be, it's 1/12 per hour. It is that way for 12 hours, and it can't be anything else. So the probability then that the time is between 2 and 5 is what we're dealing with. And that probability then will be the integral from 2 to 5 of our probability density function with respect to x. Okay, so if I evaluate this, I'm going to get 1/12 of x evaluated from 2 to 5, which is 5/12 minus 2/12. Well, 5 minus 2 is 3. And that works out to be 1/4. So what's the probability? Well, the probability is 25% of the time, that's where the clock is going to stop. So all things being equal, if we just let the clock run until it stops running, 25% of the time it's going to stop with the hour hand somewhere between 2 and 5. Okay. Now, I want to back up for just a second. You might say that the context of this problem doesn't necessitate only the hour hand between 2 and 5. You might say, well, it has to be between 2 with 0 minutes and 5 with 0 minutes. So now we're bringing in, well, what about the minute hand? Where's the minute hand have to be? Well, if we were to do that, all that would do is take each one of these sections and divide it into 5 minutes, right? So now instead of there being 1, 2, 3, now we'd have 5, 10, 15, 20, all the way around to 60 sections. So what would happen is our time intervals, instead of being from 0 to 12, our time interval would be 0 to 60. But the exact same thing would happen here. We would go from 60 to 0, the distance between those two things, so it would be 1/60th. And then our limits of integration, if we're at 2, well, that's 10 minutes. If we're at 5, that's 25 minutes. So what we would have is this problem would become, if we're going to account for minutes also, the probability that x is between 10 minutes and 25 minutes, because that would be 2 and 5, is going to be the integral from 10 to 25 of 1/60th, if we wanted to keep track of minutes. So whether you're keeping track of minutes or hours, we're going to end up with the exact same result, because if you evaluate this, you're going to end up with 25 minus 10 in the numerator, just like we ended up with 5 minus 2 in the numerator here. Well, 25 minus 10 is 15, and 15 over 60 is exactly 1/4. So we get the exact same probability. Whether you divide it up with minutes or hours, it doesn't matter. For that matter, we could come back here and we could do seconds. And now we would just have to keep track of more, right? Because I don't know how many seconds there are. What is it? 1,800 seconds in a 12-hour period. So whatever it is. So we could do this all day long. No matter how accurately we're keeping track of time, it wouldn't change anything. The odds of it being between, or the probability of it being between 2 and 5 is always going to be 25%. So this is our first example. And this is an example in which we talked about, going back to the last video, the idea that if I'm between two numbers, then my probability just simply becomes 1 over the distance between those two numbers. And then I can calculate from there to determine my answer. So this is the first type of problem that we'll look at. So our next example is coming from a book that's designed specifically for IB. And in this particular book, they have a problem that states that there is a continuous random variable whose probability density function is given by this piecewise function. And they ask us to find the mean, the median, and the mode. Okay, so let's take a look at these. The mean, this was a problem, or this formula was a formula that was in your formula booklet. the booklet that's provided for you during the test, and so that's not a formula you necessarily would need to memorize. The mean formula was that we're going to do the integral from negative infinity to infinity of x times f of x dx. Okay, well, we can see in this particular case, because it's 0 everywhere outside of 0 to 5, then this is going to simplify to be the integral from 0 to 5 of 3 over 175 times negative x squared plus 2x plus 15. Now, all of that is my f of x. Don't forget, easy thing to forget, I almost did it myself, that f of x needs to be multiplied by x, and then dx after that. So this is the integral that we will need to be evaluating. So let's take a look at how I would do this. Okay, so what we have right now then is that my mean is going to be the constant 3 over 175 can pop out. And then the x can distribute to the other terms of my polynomial. So I'm going to get a negative x cubed plus a 2x squared plus 15x dx. Okay, so that would be my first thing. When I integrate this, I can just use my polynomial rule. So I'm going to get 3 over 175 times a negative x to the 4th over 4 plus a 2x cubed over 3 plus a 15x squared over 2, all evaluated from 0 to 5. Okay. Now, for the sake of time, I'm going to go ahead and just finish this up on the calculator. I would say in this case, this is probably stretching the limits of what you'd be expected to do without a calculator, but I think it's fair game. 5 squared is 25 times 15, and that's kind of pushing it a little bit, but maybe. 5 cubed is 125, and then 5 to the 4th is 625, right? So those are things that we could do. But I think when we start pulling in those fractions, though, it's going to become a little bit less convenient. So according to my calculator, the answer will turn out to be that mu is going to be, actually I'm not looking at the calculator, I'm lying to you. I'm actually just looking in the textbook that I took this problem from. And according to the textbook, we should end up with, sorry, lost the page. Here we go. We should end up with 55 over 28. Okay, so that would be our mean, our expected value, 55 over 28. Okay, so there's our first. So the formula that we had from the previous video for the median states that 1/2 of the data is going to be somewhere between negative infinity and the median for f of x dx. This time there's no x. But we talked about that sometimes it's easier to do an integral that involves a positive infinity. That's 100% up to you. That's your choice. However, in this case, we really don't need to do either because, as we discussed in the previous problem, we know that all of our data is between 0 to 5. There's no data outside of that range. And so really what this becomes is that half of the data lies between 0 and m, and the other half of the data lies between m and 5. Now, if we write it this way, suddenly I think that the easier option is this option, right? Because I'd rather subtract 0 than have to distribute a negative through my m and then solve with that business. And so I think this becomes the version that I would rather solve. So if we plug in our actual f of x was 3 over 175, 0 to m, negative x squared plus 2x plus 15 dx. And so no extra x this time. So when I integrate this, I'm going to end up with a negative x cubed over 3 plus x squared over 2, but then the 2's would cancel. And then 15x. And I'm going to evaluate this from m to 0. But notice what happens when I plug in 0. These all go away. So I'm just simply left with all of my x's turning into m's. Okay? Now I think what I would do is to go ahead and combine these fractions together. So I would divide both sides, I think, by 3 over 175. So when I do that, that's going to give me a 175 over 6 equal to this stuff. And then if we were in a situation where we had to solve this by hand, I would want to get rid of my fractions. And I also would want to move all these terms to the other side so that my leading coefficient was positive. So what I'm going to do is I'm subtracting or adding all of these things to move them to the other side. And then I'm also going to multiply through by a 6 to get all my fractions to cancel out. So this is going to become a 2m cubed. When I move it to the other side, it becomes positive. This is going to become a negative 6m squared. This is going to become a negative 90m. And then I have the 175 that's already on that side, so it stays positive. Okay, so we can try and solve this by hand, depending on if it's on the with a calculator or on the no calculator half of the test. If we were going to do this by hand, we would try to do it with grouping and see what happens. However, I can see what the answer is because I've got the textbook right in front of me, and I can see that the answer turns out to be not super convenient. So I'm assuming that although it looks like it might work with factoring, I'm not sure that it does. What's 175? Yeah, that's not going to work by factoring it with grouping, so I just double check the numbers. So because it doesn't work, we're just doing this on our calculator. So if I were to graph this thing and find the x-intercepts, find where it equals 0, what we end up with then is that the m turns out to be approximately 1.857. Remember, rounding off to 3 significant figures would give me that. Okay, so that becomes my median. So we had a mean of 55 over 28 as a fraction, or as a decimal, excuse me, that would be 1.96 approximately, and then a mean of 1.86. Okay, so now we're going to find the mode. Our f of x was equal to 3 over 175 times negative x squared plus 2x plus 15. The mode is going to happen at the maximum of that value, so I need to find f prime. So the constant stays there. This is going to become a negative 2x. This is going to be a 2. 15 goes away when I take the derivative. Setting that equal to 0, I can just simply get rid of the fraction, right? Divide both sides by a fraction. 0 divided by anything is itself. And so we end up with x is equal to 1. Okay, so this becomes our modal value, x equals 1. I suppose we might want to say, well, let's verify that that is indeed the case. But if we think about the fact that I've got a parabola that's opening down, right? So my endpoints are definitely going to be below my peak value. So I think we're going to be all set. But if I were to double check this, if I plug in a number that's a little bit less than 1, like 0, I get that this thing is positive. So numbers less than 1 are increasing, right? Because I get a positive derivative, so it tells me I'm increasing. If I take a number a little bit bigger than 1, like say 2, I'd get a negative 4 plus 2 is negative 2. A negative times a negative is a negative. So my derivative is negative. That tells me that after 1, I am decreasing. So sure enough, 1 was a maximum. And so therefore, that's our mode. Okay, so this would be the process. I suppose on this problem, as a side note, I guess the other thing that you could do is you could go back, because it's a parabola. We know from algebra class that the x-coordinate of the vertex is this, right? So negative b over 2a, negative b over 2a. I'm going to get the exact same answer. Okay, so you can approach that a couple different ways, but that's what we end up with for our mode. Okay, there's one more thing I want to mention before we move on to our final example. When we did the median just a minute ago, what we did was we set up the integral like this. So keep in mind as you're working through the homework, if they asked you instead to find, for example, the lower quartile, if you wanted to find the lower quartile, 1/4 of the data is below that value. And so it would have been exactly the same as what we did in the example, except for instead of this being a 1/2, it would have been a 1/4. That would have been the only difference. Upper quartile, this would be a 3/4 or a 3/4. Okay. What if they wanted to find the, the 90th percentile, right? So the 90th percentile is greater than 90% of the data. So I could dummy variable here, whatever, doesn't matter. I could solve this now, and solve that for x would give me the value for the 90th percentile. So keep in mind that if they're asking you for median, lower, or any sort of percentile, all of these problems are going to be exactly the same. The only difference is what is going over here. Median is half, so it's 50th, 25% for the lower quartile. If they ask for the 90th percentile, you'd put a 0.9, whatever it is. And of course, for all of them, you could also do the alternate. If I'm at the 90th percentile, 90% is below, but that means 1% is above. And so again, choosing dummy variables, because it doesn't matter what I put, that would be an option, an alternate option. So these would both find the 90th percentile. Okay, so that's just a quick note before we get to our final example. Okay, and here's the final example that we're going to do. This is coming from the same textbook, this book right here, and it's asking us to find both the variance and the standard deviation for this particular probability density function. Now the variance, you might recall from the first video, this is a formula that's in the IB formula packet, and the variance formula is equal to the integral, actually this was one that was written two different ways. The integral from negative infinity to positive infinity of the quantity x minus mu, quantity squared, times f of x dx. That was one way that it was written. And of course mu represents our mean, the expected value. But we could also take that thing and rearrange it, simplify it slightly, and what we end up with is x squared times f of x dx minus mu squared is what we would end up with. And so it doesn't matter which one of those forms you use, they will both work. In this problem, of course, like we've talked about, my limitations are all of the data is between 0 and 2. There's no data anywhere else. So this equation simplifies to just simply go from 0 to 2, no matter which of these two that we choose. I'm choosing this one for right now because since we're working with a polynomial, this is going to end up being an integral that I can do by hand, and I would rather not have to FOIL this out and then combine it with this thing before I integrate. This will be much easier to work with. So either way, whether I'm using this formula or this formula, it's obvious that I have a problem right now. I need to know what the mean is. Before I can evaluate this, before I can evaluate this whole thing, I need to know this thing. So before we can find the variance, we also then have to find the mean. And this integral was x times f of x dx. And on this problem, all of our data is between 0 and 2. And so we're going to work with this. Okay. Now we've done an example of that already. And because this is a polynomial function, it is something we're going to be capable of doing by hand. So I'm just going to take the answer that the authors of this textbook found for us. It turns out that that's exactly equal to 6/5. Okay, so I'm just getting that from the textbook. That's something you should be able to do. So if you want to pause the video right now just to confirm that you get 6/5, feel free to do that. But that's what you should end up with. So that means that our variance is going to be the integral from 0 to 2 of x squared times f of x, which is 3 over 4 x squared 2 minus x. and then minus 6 over 5 squared. That's what we should end up with. Okay. Now, again, this is a integral that is just a polynomial, so I could do an x squared times x squared gives me x to the fourth, and I could distribute this in here. So I'm going to get a negative 3 over 4 x to the fifth, and then a 3 over 2 x to the fourth, and I can integrate that using my polynomial rule. This is something that we can totally do by hand, and we're going to be fine. But for the sake of time, because this is already getting longer than I was hoping it would be, we will end up with 8 over 5 for the integral, and then a 6 over 5, and that turns out to be a 0.16. We could write that as a fraction, but it's just easier to write it this way because for the next step. So on the next step, they want us to find standard deviation, and this is always equal to the square root of variance. So for standard deviation, on this particular problem, I'm just taking the square root of 0.16, and of course that equals exactly 0.4. And so these are my two answers. The variance is 0.16, and the standard deviation is 0.4. So these are the types of problems that IB is going to be expecting you to be able to do, in addition to proving that something is a probability density function, which we did in the previous video. As I said, if I have time, I'll try and post a video with some normal curve information, but the day is starting to get away from me, so I may end up posting that tomorrow or perhaps even not at all. I hope these have been helpful for you. Thanks for watching, and good luck.